Hi, thank you. And thanks to Basho for hosting this conference, great conference. So I'm a senior software engineer at Netflix. I'm Ryland. This talk is about technology that was developed when I was at a previous startup called Skydeck. And it's client software that's all about structuring your data in Riak in such a way that you can make very fast queries to it in real time. So avoiding the use of things like MapReduce and secondary indices, which tend to slow it down. It's all about serving real-time APIs. So Skydeck was a mobile application built around photo sharing. It consists of users who have profiles and can do the usual things, post photos to their profile, like other people's photos. And essentially, when you go to the home screen, you have a stream of other people's photos who maybe you've liked their photos or they're popular. And you can click on them and interact through messages. The back end to the application is written in OCaml. Yes, OCaml. Isn't that like something French PhDs write software in and then forget about? Yes. But it's also a really cool language, and I hope through this talk you'll see a little bit more about what it's capable of. So all our user data is stored in Riak using the excellent protobuf client for Riak written in OCaml, written by Dave Parfit. And we use Redis, like many other users here, for caching ephemeral data. So our experience with Riak. In general, key value lookup, great. Super fast, scales well. But when you start to make more complicated queries using secondary indices, range queries, MapReduce, those are great if you're running it as a sort of asynchronous job. But if you're actually serving a real-time REST API, we found them to be a little bit unpredictable and just a little bit, the latency was just a little bit too great for us. We needed to find another solution. For example, you have a set of friends and you want to know, okay, which photos have my friends liked lately? Maybe you have one friend that's been really active lately and they have a whole bunch of photos and the other ones haven't logged in for a while. You want a quick way of making that query without going to every friend and searching through all of the photos that they've liked and combining that all in memory. So denormalization, caching, search can go a long way, but we found ourselves wanting more, sort of a more direct access to the actual data. So one possibility, which we've seen people do, is sort of store the data in a linked list. So each of these nodes in the linked list is a key value pair in Riak, and maybe you use links to point to the next node. And you can start the list some predefined key, call it head or some user ID, and you can walk the list and get a stream of photos that way. Okay, that's great for a small list, but if the list has 10,000 photos in it, then you're going to have to do 10,000 reads to get to the actual last element of the list, and that's problematic. So this one has really good performance in adding to the head of the list, querying at the very front of the list, but beyond that, not so good. So we wrote this library, and the intention is to abstract away this problem, how to structure data in Riak so that you can make these kind of queries. It's implemented, as I said, on top of the OCaml protobuf client. And a lot of the work is inspired by a book called Purely Functional Data Structures, which came out in 1996, but it's still a really awesome book and pretty much the only book of its kind geared towards functional data structures. So why functional data structures, other than the fact that we were already using OCaml and Riak's written in Erlang, that's cool, but why did we make that decision? I should mention that the approach we've taken is very concurrent. It's very thread-heavy. So we use a library called lightweight threads, LWT, in OCaml, which is a monadic concurrency library, and it gives you something like the I/O monad in Haskell will give you sort of a way to structure your concurrent computations so that you can sort of go ahead and do everything you possibly can at once and then wait for them all to come back and proceed. Whatever you need to come back in order to do the next step of the calculation, you can wait for. And another really nice library written by Martin Jambon, which is YoJSON and BNU for serialization, into JSON and a binary format, respectively. So what is a functional data structure? Well, it's a double-edged sword. Functional programming doesn't allow you to do destructive updates. So once you write a value, that's the value for the life of the program. You can't go back and modify it later. So it can be hard to imagine how could you possibly write a data structure in a purely functional language. It's almost like confiscating a master chef's knives. But the flip side of that is knives can be dangerous when misused. And the benefit you get in a purely functional setting is there's no need for locking because there's no contention. You never have two resources competing for the same, for access to the same value because everything you write is immutable. And you also get persistence for free, if you can imagine, because once you've written the list, that list is going to remain in memory forever. And anyone who comes in later, days, weeks later, is going to be able to read exactly that list, no matter what other changes in the system have gone on in the meantime. So here's your classic imperative linked list. If you want to insert a value, B, you traverse through the list till you find the right place. You make the new node point to C, and then you fix up the pointer to A to point to your new node, and you have your new linked list. But notice that in the process, you've destroyed the original list, which is one of the inputs to that function, because you no longer have a list A, C, D. Anyone who was doing something with that list is screwed. In a functional language, it's a little different because you can't modify A to change it to point to your new value B. So what you have to do is you copy all the nodes that are on the path to the node that you've just inserted, and you create an entirely new list that shares the tail with the original list, so you don't have to copy everything. But preserves the input, it preserves the old list ACD so that that can continue to exist and other people can continue to do it. And if you want to undo that operation, you can simply set your head to the old A, and you'll have your old list back. But as I said, a linked list is not the most efficient data structure for the reason that if you want to access the 10,000th element, you have to do 10,000 reads. So something a little more efficient is a binary tree. So if I want to add an element into a binary tree, I only have to do a number of reads logarithmic in proportion to the size of the tree. And in the same way that I would copy the nodes on the path of the linked list, I copied the nodes on the path to the new element G that I've added, and have them point and have them share the unchanged elements with the original tree. So the amount of overhead in terms of extra data can be managed with the right data structure. So in OCaml, this is the way you might implement a tree of type A. So in our node, we're storing some value A, and then there's two pointers to the left and right subtree. If I was going to put this in Riak, I would make those links or store it within some sort of JSON blob so that I could later on go and access those subtrees. And it is an improvement over a linked list. However, if I keep adding bigger and bigger values, you can see this right subtree is going to continue to grow. And eventually, I'll just have a linked list. It's just going to be an n complexity to access that last element, because the tree is going to become unbalanced. So while this is a good start, it doesn't quite work in production. So what we need is a way to balance the tree, essentially. And there's a million ways you can do this. But the one I like the best, using OCaml's type system, is simply to make an unbalanced, to use such a type so that an unbalanced tree is actually unrepresentable. So there's something called a 2-3 tree, in which we move all of the elements to the leaves of the tree. And this is a very interesting data structure because it's what's called a nested data structure. So if you see, the very first layer of the tree contains the elements of the type that we've provided. But the higher layers of the tree contain types of A node. So it's actually a 2-3 tree that contains nodes of our element. And then the next level up contains nodes of nodes, and so on. So what we're saying is that the path from the root of the tree to any element is going to be identical, and hence the tree is always going to be balanced. It's impossible to create an unbalanced tree in this data structure. So cool, we're on the right track here. And we have the additional benefit that storing all the data in the leaves of the tree means we can write that data once and forget about it. And then within the tree itself, we can store information about that data to make it really easy for us to look it up. So if we wanted to do a priority queue, we could store a priority and maintain the maximal priority at the top of the tree. If we wanted to do a random access list, we could provide the sum of the number of elements underneath that subtree. But we've actually made one thing worse, which is that just adding an element to the top of this data structure now requires logarithmic time, whereas with a simple linked list, it was a constant time operation. So we would like to be able to add and remove elements from either end in constant time. So there's one further refinement of this data structure, which is a relatively recent invention, which is finger trees. This is based on the 2-3 tree, but provides efficient access to the nodes at the left and right ends of the tree. It was invented by Ralph Hinza, who happened to be my supervisor, really smart guy. And it's sort of a general purpose data structure in that it can serve, depending on the annotation that you put on each of the levels of the tree, it can serve as a priority queue, search tree, interval tree, all sorts of cool things. So it's sort of ideal for implementing other data structures. And actually, it is what the sequence data type in Haskell is implemented with. So a 2-3 tree, if you can imagine picking up the left and right trees, the TH and RE, and sort of lifting them up and combining the matching subtrees together, you make what's almost like a finger sort of reaching deeper and deeper into the nested structure of the tree. So the top is a 2-3 tree, and the bottom would be the equivalent finger tree. And as you can see, we have very fast access now to the head and tail elements. But the further deep we get into the center of the list, which happens to be sort of the least accessed part of the list in any case, the less efficient access we have to it. So there's a few different ways we could slice this to put it into Riak. The one that I've gone with in this library is this. Each nested layer of the tree is represented as just one key value pair in Riak. And each of the leaves of the tree, the elements themselves, are stored on their own. So in that way, the same elements can be indexed in multiple ways, can be part of multiple different finger trees, depending on how you want to query them. So in this case, we might store these orange nodes in one Riak key. This would be the next layer. We store all of these and their corresponding annotations in a different index. And then the end of the tree would be nil, signifying that there's no deeper tree to move down into. This is another example of a nested data type. As you can see, the deep constructor takes a node of the element that's passed in. So each layer of the tree is a node that's one layer deeper. So measurements now are the way that we can provide efficient lookup information, lookup access to this tree. So we want to provide some sort of measure of the data that's underneath it so that with every lookup, we don't have to read every value of the tree and sort of compute it in memory. We can just cache those values, read the cached value, and we know exactly what's underneath that tree for our purposes, and we know we don't have to traverse that entire area of the tree. So for example, let me go back. So what we have to provide in order to do this is called a monoid, but what that simply is some type that has a 0 element and a way to combine elements in such a way that you can build up the annotations using the existing annotations that you have already. So an example of this would be, say, the natural numbers. If the type T was the natural numbers, 0 is just 0, and the combine element could be any associative operation. So plus, for example, is a monoid. And a measure is just a way to take the type that you're storing into the tree and translate it into this monoid type. So I'm going to give a more concrete example, which is the random access sequence. So this is a data structure that we build using a finger tree and provide to the user of the library. So as I said, the monoid here is an integer. The 0 is 0, the plus is the plus operator, and each element counts as 1. So what we're essentially doing is providing array-like access into the subtree. So in this way, it's very easy to look up for a particular array index which subtree we need to descend into. So if we just go from left to right, the first subtree has the first 2 elements, the next one has the following 9, and the final subtree has the remaining 3. So if we were looking for the 10th element, we know we'd have to go into the middle tree. We can get even fancier with combining monoids in the sense that a user can provide as input into the library their own monoid that does some sort of measurement of their data that they're interested in looking up. So if you're storing, say, a JSON blob with a huge, with all the data representing a user, you might be interested in looking up that user by their last name. So you might just extract the last name from that blob and then compare it using an alphabetical comparison. And in the library itself, we can combine that with the size monoid in such a way that we can actually, using the same index, and we can look it up in 2 different ways, either through an array-like lookup or through the user query on last name. So that application, an ordered sequence, the annotations might look something like this, where first, each annotation is a pair, and the first element of the pair is the greatest of the sub-elements, and the second is the sum of the sizes. So you can see in this way how it's quite easy to look up any given element either alphabetically or through its array index. And this is really good. So this means that we have constant time append at the front and rear of the list, constant time measure of the entire list using some property that's passed in from the user, and lookup that's even better than logarithmic time, because depending on where the item is in the list that you're looking up, if it's towards the ends of the list, you have an even better performance in doing inserts and lookups. But inserting deep into the middle of the list is going to be a little bit more challenging. So one other application of this that I wanted to talk about is taking this data structure that you've created, stored in key value pairs in Riak, and querying in different ways, sort of translating the logic of the query from the library itself to something that's provided by the user. So in this case, we want to take a structure that's stored in Riak and translate it into a sort of lazy stream that can then be combined in the user's program. So we have a function already to iterate through each of the nodes in the list. It's quite easy to write. And this is the possible implementation of the toStream function, which takes takes the key representing the head of the list and returns a stream of the user's elements. And the way we do this is using mvars, which is a concept that originated from Haskell, which is a single message mailbox variable that's used for communications between threads. And what an mvar is just essentially a mailbox where you can put a message in. Further puts will block until that message is removed, and another thread can consume the message, and a consume will block if the mailbox is empty. So in just a few lines of code, now we've given ourselves the ability to do something like this, which is write an activity feed which combines multiple streams from all your different friends. So say you have hundreds of friends. All we need to do is transform them into lazy streams. So we're not actually reading and writing anything, only the first element of the list. And the remaining writes are going to wait until some sort of combining process triggers the remaining element to be inserted by pulling from that mailbox. So you might have 100 friends, and you can pull all the recent activity. You go through the list and look for the most recent one and pull it out, and then check with the new one and pull it out so that you have a combined feed in order of all the activity that your friends have been doing in pretty much the most efficient way possible. So I wanted to break out into demo because it's a lot of graphs, but I think when you actually see it working, it's a lot more exciting.
Font size.
Sorry?
Font size. I can read it.
Sorry.
But just barely.
Anybody know how to do font size in Emacs? Let's search. I'm just gonna have to go with this. Sorry if it's a bit small. Is there a way to just blow up the screen?
Meta set face attribute. Meta X. Set face attribute. Single tick default.
Is that a No, it's not gonna. Okay, I'll just go with this. Okay, so we need to provide some sort of pool of threads of protobuf threads with which to access Riak. So the first command I'm going to run is just setting up a LWT pool, which is a pool of 100 threads here, just pointing to the Riak that's running on my local host. And then we just set up an OCaml module that expresses the ability to connect with something pulled from that pool. So for the element we're going to use, let's just go with a simple int. We need to provide a toString and of string and some bucket in which to put our tree. And then we can create a random access sequence. So this is the example I gave where this is just going to be array access. So it's going to combine the size of the subtrees with each element representing one item. So suddenly we have all these cool ways to access our Riak data. We can cons and snock, we can check the first and last elements, and we can do all sort of cool functional programming stuff like fold left, fold right, map, and so on. So we initialize that list to an empty list. If we then check the size of it, it's predictably enough is 0. Now you can provide your own key if you have some sort of key structure that you want to use, but that's an optional value. If you don't provide a key, it's just going to generate a random key. So you can see here, it's the head of the list is now stored at 6H5, whatever hash value that is. So the next thing I might want to do is cons onto the head of that list. And as you can see, it's provided a new head because all of this is non-destructive. So now this head is the new head of our list. It contains a single element, which is 1. If I add a couple more elements, and then do a head, you can see it's the last element that I just added. I can also check the last element in the list. Oops. I said head by mistake. The great OCaml syntax. So the last element of our list is 1, as we would expect. So let's do something bigger. Let's just say take a list of 100 elements, and now I just want to express that we can treat this data, although it's being stored in key value pairs in Riak, we can treat this almost exactly as if it were a list on our local computer. So we can do a fold right over the current head and just continue to add elements and use the new head. So this operation just added 100 new elements to our list and provided us with a new head. And now we can do things like look up the 50th item in the list. Or do a page query. So let's take the first 40 items. I should really say 0. So you can, it doesn't matter what you provide, it provides very efficient paging, which is on a large set of data stored in Riak is a very intensive operation using something like a secondary index, as many of you may have experienced. So what we found is that using something like this provided, first of all, predictability in the sense that we could write API queries against it that would return in very consistent fast times versus a MapReduce or something, depending on what else is going on in that node, could take a long time and end up timing out the API response. Let me do one more thing, which I don't think I had in here. Which is something like this. So I want to compute some kind of function that runs across every item in this list. So in this case, I want to sum up the values that are contained in every item in this list. So I can use the fold left operation and provide some sort of accumulator. So starting at 0, I'm going to fold across the entire list and just add each element to that accumulator. Something that a MapReduce does. Okay. And very quickly, we've got the answer. In terms of what's actually stored in Riak, it's nice to visualize. So if I go to the head of the list, I can see what that actually consists of. It consists of so it's some kind of JSON representation of the OCaml type that I had previously showed you. So this is a deep node. So 103 is the total number of elements in the list. And then there's a left subnode, which has the first elements in the list, and then a right subnode that has the final few elements, and then another deep node, which points to. This sum is another deep node with the address of the next layer down in the tree. So that's one approach. And based on other people's presentations this year and last year, I know a lot of people have similar problems in just figuring out how to store your data in such a way that you can do what you want to query it later on without sort of do a complete bulk rewrite of the data. And search and these sort of things are great, but ultimately only get you so far. So things like this are just an interesting way of structuring your data so that without preventing you from doing things that you normally would want to do, the sort of queries you might normally want to run give you new and sort of faster ways to query the data. So, thank you. Any questions? Yeah.
Yeah. What type of conflict resolution mode are you running Riak in, or do you deal with siblings?
We don't. Yeah, we have sibling resolution turned off.
Okay.
So that's one thing, sort of future work that could be done on this. Another is garbage collection, because as you can imagine, it's a problem in functional languages. Every time you copy something to a new element, you've generated garbage. And if you're not using the old list, then you need a way of eventually cleaning it up. Fortunately, in this structure, most of the garbage generated is just very small, so it's not really going to fill up your disk anytime soon, but it's something you might want to think about for later. And then another thing I had thought it would be translating into Scala to provide a sort of bigger user base for this sort of thing, because I know not many people are running OCaml, although it's a great language to develop this sort of thing in. If you're looking to actually have users, it's probably not the best. Okay, great, thank you.